So our next speaker is Kevin Benitez. He is an ACI student member who graduated with a degree in structural engineering at Polytechnico di Milano in Milan, Italy. He received his Bachelor of Science from the Universidad San Francisco de Quito in Quito, Ecuador, and his research interests include behavior of reinforced and pre-stressed concrete under combined effects, concrete bridge design, and evaluation of existing concrete structures through load testing and non-destructive testing techniques. And with that, I'd like to hand it over to Kevin Benitez.
Okay, so thanks, Gary, for the introduction, and thanks to everyone. So I will present you a torsion design example of a prestressed concrete girder bridge that was developed also with Eva Lansot. So, yeah. So here I'm the overview of the presentation. I will start giving you the description of the design task. Then I will give you also a rough overview of the design procedure followed for this specific bridge. Then I will show the detailed design procedure for the ACI 3.18.14 design code. Then I will present some design results. Finally, the comparison of design results with other design codes that I will speak later which codes were also used for the design, and some important remarks and conclusions. Okay, so the design task, in this case the bridge, is a 3-span cast in place post-tensioned multi-cell box girder bridge. It has, as mentioned before, 3 spans. The first one of 126 feet, 168 feet, the second span. The third one, 118 feet span, that gives us a total length of 412 feet. This bridge will be subjected to combined effects of flexure, shear, and torsion. Also, here we have the view of the box girder that is the composed bridge. As I mentioned before, is made of pre-stressed concrete, and the loads that act on this box girder are its self-weight, a wearing surface with a thickness of 3 inches. And for the load model, we choose as a live load model, the AASHTO LRFD 2017 HL93, that consists of a design truck plus the design lane load. As materials, we use concrete with a FC prime resistance of 5 KSI, steel with a yield strength of 60 KSI, and prestressing steel with a ultimate strength of 270 KSI. So the design procedure, first we perform the structural analysis with a commercial bridge design software in order to get the envelopes for all the actions on the bridge. I mean the bending moments, shear, and torsional moments. And then the design for flexure limited state that consists on the prestressing steel was done according to AASHTO LRFD 2017 using the load combinations and factors provided by this design code. Then the design for shear and torsion was developed according to the following design codes: AASHTO, the ACI 3.18.14, Eurocode 2, and the FIB Model Code 2010. So going a little bit ahead, the design procedure, we start with the prestressing steel. In this case, it was proposed a parabolic tendon profile for the bridge. The prestressing losses that were calculated, including instantaneous and time delayed losses, were of 25%. A total jacking force of 9,300 kips was computed, and this gave us a required area of prestressing steel of 46 inches squared that was distributed evenly over the cross-section of the bridge. So here I will address the steps for the computation for the design using the code ACI 3.18.14 that is in the paper included as a detailed design procedure. So first of all, we start determining the factored loads based on the provisions given on Article 5.3.1. And that's an initial step. And also the second step, the section properties. I mean, the gross area, the moment of inertia, centroids, and stuff. Then as a third step, we should check the flexural resistance provided by the tendon layout that was the one shown before. That in this case, it was actually the design made based on what was the AASHTO design code. And then in case of it is required, there some mid steel should be provided for this flexural limit state, also to avoid additional cracking on the cross section. Then we enter into the part that's of our interest, I mean the shear and torsion design. So as a fifth step, that will be the first step for the shear and torsion design, we should check if torsion can be neglected for this cross section. I mean, if the effects the loads acting on the bridge produce enough torsional moments that will require the design for torsion on the for this cross section. This is based on the provisions of Article 22.7.4. Then, if torsion can't be neglected, if we have to design also for torsion, we should check if the dimensions of the cross section are adequate to receive the combined effects of shear and torsion. Then we should calculate the required area of transverse reinforcement for shear and the required area of transverse reinforcement for torsion. So then once the required area is computed, we should check the maximum spacing for the provided transverse reinforcement, complying with the articles mentioned there. Finally, calculate the required area of longitudinal reinforcement for torsion that would be provided as an addition for the longitudinal reinforcement that was computed on step 4 for the flexure limited state. And finally, check if these provided areas of transverse reinforcement and longitudinal reinforcement are in effect larger than the minimum requirements by the design codes. So the design results that are obtained using the ACI 31814 design code were the following. As a required area of transverse reinforcement for torsion, we found that the required area was 0.04 inches square per inch. But then, since this cross-section is subjected to a combination of both shear and torsion, we should, for the exterior webs, provide the combined reinforcement for both shear and torsion. So that's what is mentioned there as required transverse reinforcement for this combined shear and torsion. That in this case was a total of 0.20 inches square per inch, and the provided reinforcement was number 5 stirrups at 3 inches spacing on center. They are shown here on these details that are also included on the paper. Then the required area of transverse reinforcement for torsion and flanges that are, the top and bottom slab of the box girder. Here the computed values were 0.035 inches square per inch, and we provided number 3 stirrups at 6.25 inches on center. And the required area of longitudinal reinforcement for torsion was computed as 83.3 inches squared. So we provided 106 number 8 bars that will be distributed evenly over the total exterior, both webs and flange of the box girder. But we will place a concentration on the corners, since those are subjected to, a concentration of stresses due to warping of the cross section. And yeah, here now I'm entering to the part of a comparison of design results. The first comparison that was made is regarding the cross-section dimensions for each design code. As I mentioned before, one of the steps that is required by each design code is to check if the dimensions of the cross-section are adequate. So for example, for ACI 31814, given the acting loads, I found that we have to increase the exterior webs from 12 inches, that was the initial design, to 19 inches, and the interior webs to 15 inches to resist both the effects of shear and torsion. In the case of AASHTO, the cross-section is kept as the same. For the case of the Eurocode 2, we choose to do the design considering 3 inclinations of the strut. Also for the FIB model code as a level of approximation 1. So that I will explain later on what's the logic behind this. So here we can see that both the ACI 31814 code and the model and the Eurocode 2 give a cross-sectional gross area larger than the rest of the codes. So in this case, for this design, it could be said that maybe they are a bit conservative on these kind of cases. And then the comparison is made regarding the reinforcement ratio and total weight of reinforcement for each design code. So first, we can see the comparison that it's done between the total weight of longitudinal reinforcement and the total weight of transverse reinforcement. So for example, here I can take the Eurocode 2 result with an inclination of the strut of 22 degrees. As longitudinal reinforcement, the required value is actually very high, 43.6 pounds per inch. But the total weight of the transverse reinforcement required is actually the lowest from all the other design codes at 9.6 pounds per inch. This is, because of the inclination, changing the inclination from a low inclination to a 45 degrees inclination, it can be seen that it increases the required area of transverse reinforcement, but it decreases the required area of longitudinal reinforcement in this for the model used for the Eurocode 2. Among these values, it could be seen as well that the most balanced solution is given by the AASHTO LRFD 2017, and also the model code, FIB model code on its level of approximation 3. Here we can it can be remarked that both design codes, the provisions are based on a simplification of the modified compression field theory. So it's a more refined design procedure that will eventually lead to a more refined also solution for the design. Then, okay, so we are arriving almost to the end. So as a summary here, this paper presents basically the detailed design of a cast-in-place post-tension concrete box girder, the detailed design steps for the ACI 31814 code are presented, and the design results according to this code, the ACI 31814, are compared with those of AASHTO, Eurocode 2, and FIB Model Code 2010. This is briefly what's presented on the paper that is included on the special publication. And finally, some important remarks regarding the used codes. As it was said before, the ACI 31814 uses a space truss analogy that is based on a thin wallet tube. AASHTO LRFD 2017 and the FIB model code at its level of approximation 3 use both a simplification of the modified compression field theory, and Eurocode 2 uses a variable angle truss model that uses the same analogy of a thin wallet tube. Then the FIB model code, it has an approach based on level of approximation. So we start from a level 1 that gives us, a really not so refined solution that is also similar to the one in Eurocode 2 that is based on a variable angle truss model. So then we pass to the level of approximation 2, that is the generalized stress field. And the final level of approximation, level 3, it's a simplification of the modified compression field theory. There is also for this FIB model code level 4 that will be basically used a finite element model. But here for this paper and this publication, we just focused on the first 3 levels of approximation. Finally, a little comment on the design results. The ACI requires more steel and concrete. The provisions are more conservative. Level of approximation 2 and 3 of the model code and AASHTO provide the most balanced solution. And also because since the design example provided was of a bridge, and I mean AASHTO is a code specifically thought for bridges, then it's maybe it has more refined solutions to those kind of problems. And then Eurocode 2, as a recommendation, it could be said that since we are based on a variable angle truss model, we can use a mean value between the minimum and the maximum allowed for the design code in order to have as well a more balanced solution. Finally, one important aspect of this on this paper was that each code has its own live load models. Here we use just the AASHTO live load model that consists of the HL93 truck plus design lane load, but each design code has different live load models. So that should also be taken into consideration, because the initial idea was to have one load, one type of action in order to just compare how each code differs on the provisions and the final results. And well, I think that's it. Thank you once again for your attention, and if you have any questions, I will be glad to answer them.
All right, thank you, Kevin, very much for that great presentation. We will probably have time for maybe 1 or 2 questions. I guess I had a question when you showed us that the table with the different widths calculated by BWs, calculated by the different methods. Why do you think that ACI 318 was so much thicker than, say, AASHTO or the model code?
Well, as I mentioned there, it depends on the model that's used. For example, on the model for modeling the torsion. For example, AASHTO and the model code on its level of approximation 3, the equations are based on the simplification of the modified compression field theory, while ACI also has a different model for torsion. As well, also the ACI considers just the contribution of the concrete to the resist of torsion and shear. So that's why maybe it has a larger increase on the width of the exterior and interior webs.
All right, thank you.
I'd like to as well ask you a question. And you see it here already on this slide with the different values of theta. You've spent quite some time looking at the effect of theta. And you also addressed this in your conclusions, but could you elaborate a little bit on how all of this works together? When you change theta, how does it affect the cross-sectional design as well as the longitudinal and transverse reinforcement that you find?
Okay, so well, the first important comment about it is, as you can see, when we use theta with a lower value close to the lower limit allowed by the codes, I mean, here are the codes that are allowed to change this angle of inclination, are the Eurocode 2 and the first level of approximation of the model code. So here we can see that at the beginning we have an increase on the cross-sectional area. And as well here, as I mentioned during the presentation, there is also an increase on the requirements of longitudinal reinforcement, but there is a decrease on the requirements of transverse reinforcement. So it's maybe the reduction of theta will increase the amount of longitudinal reinforcement that is required for your cross-section, but you will require less transverse reinforcement. Then if you increase this angle, I mean, that's why I started with a low value of theta, and then I arrived to the maximum allowed limit to see what's the effect. So for example, if you increase it to the maximum allowable limit, you can see that the required area of transverse reinforcement is the larger of all the design codes. That's why the transverse reinforcement will take all the force will resist all the force from shear and torsion, but the required for longitudinal reinforcement is lower. So in this case, as a recommendation, as I said at the end, it should be to use a mean angle between the minimum and the maximum allowed by the design codes, and that would give you a balanced solution. Yeah. Thank you as well. I think we don't have.
Yes. All right. Thank you, Kevin, so much for that.
Thank you for having me.